All right, so we're going to go ahead and go back to the spec sheet again, except this time we're going to be looking at the accelerometer and magnetometer, figure out exactly how to interface with that. So let's go ahead and go again back to the table of contents and the register mapping page. Okay, so we know that the first page is pretty much all the gyroscope registers. The next few pages are the ones for the magnetometer and the accelerometer pages. So XM means it's for the accelerometer and the magnetometer, M just means it's for the magnetometer only, and A means it's for the accelerometer specifically. So let's go ahead and look through this. We can see that there's just one thing called the whoami_XM, which is pretty much the whoami register of the gyroscope, except for it's the accelerometer and magnetometer. Now, we're going to go ahead and just use this as a way to double check if we're actually interfacing with the magnetometer and the accelerometer correctly. So again, if we read this register and we get this specific output right here, that means that we are in fact communicating with the device. So we know that the register address is equal to 0x0f. But again, since we're reading, that means that the topmost bit is going to be set to 1. So if I just type in f, 0x0f, and put the topmost bit as 1, that means it's actually 0x8f is what we're actually going to be using. So 0x8f, which equals in decimal format 143. And this should be, if you look at this and actually write this binary code up, let me just go ahead and do that. So 0, 1, 0, 0, 1, 0, 0, 1. That should be 73, so it should be 73. Now we're going to go ahead and keep scrolling down and figuring out exactly which other registers we want to use. So let's go to the little option, to all the way down to when we actually see the accelerometer and magnetometer registers. So that should be went to a little bit too far out there. So it should be we're somewhere around right here. Okay, here we go. This is where we start because this is the end of the gyroscope page. So there's actually a temperature sensor on the accelerometer magnetometer, but we're not using it for one particular reason. It doesn't actually give you don't actually have a calibration curve for the temperature data, so we can't actually make sense out of the numbers that are coming out. You can go ahead and calibrate it yourself, but we're not going to be doing this for this tutorial. Status register for the magnetometer, we're not going to be using this either. This is more for to double check if actually any data came in, but we're actually just going to be reading in the data, so we don't actually want to use this register. All right, here we go. Out x/x_L_M. So this is the low bytes, and these are the high bytes for the magnetometer on the x-axis magnetic data. So let's go ahead and make sure we have this for reference, that exactly what the register is and how to read from it. All right. So one advantage with this is that the fact that these are actually the register address IDs are one after the other. So we can in fact do the multiple byte read option. So the idea of the multiple byte read option is that instead of saying that we want to read this register, then read it, and then say we want to read this register and read it, we can actually say we want to read this register and want to read the one afterwards. So we can get this one and this one after each other. So it just makes reading a lot easier. So we're going to just record the register addresses. So there's 0x08 and 0x09 are the ones we're using. So again, to do the multiple read, what you want to do is you want to make the top 2 bits 1. So since we're going to start reading from this one right here, which is the lower numbered address, we're going to go ahead and just type over here 0x08 and go ahead and put the top 2 bits as 1. So that means it's actually going to be C8 is the ID, or the thing that we're going to be transferring first, with the register address ID we're going to be transferring first. And in binary, actually in decimal, that should be 200. So let me just get this a little organized. So these are the magnetometer data registers. Okay, I'm just going to go ahead and copy paste this and go ahead and change this to Y for the y-axis. Also, there should be /H for the indicate that's the low and the high bytes. So again, this is in 16-bit as 2's complement left justified. So that pretty much means that what we want to do is we're going to collect the first byte, which is stored here, and the second byte stored here, and then put them together and change them into and put them into a 16-bit format. So we know that the y-axis is for 0x0a, whoops, and this is 0x0b. So again, we want to go ahead and add the top 2 most bits as 1. So that means we're actually communicating with via CA, so that's 202. I'm going to do this again for the z-axis. We scroll down here for the z-axis. 0x0C are the two register addresses. And then we want to go ahead and talk with this one and put the top two most bits as 1 to do multiple byte read. So 0x0C, and then I put the top two most bits. That should be CC, which should be 204 if I'm correct. Okay, 204. Okay, so we already got this one. It's going to find the other addresses. So we want to find the ones where we can adjust the sampling rate of the accelerometer or the magnetometer and adjust the sensitivity of both those devices as well. So this is for the interrupt, which we're not going to be using. So we're going to ignore this register. This is also for the interrupt as well. So we're going to ignore this one again. This is also for the interrupt. So we're going to ignore this one. Okay, offset. This is like if the data comes in and it's a bit off, you can use these values to change it and calibrate it accordingly. But we're not going to be using this one just for now. Maybe we might later, but we're just going to be ignoring these. Reference X, reference Y, and reference Z. This is for the high-pass filter on the accelerometer. We're not going to be using the high-pass filter, so we're going to be ignoring that as well. This one is just if you want to use the first in, first out data storage and the high-pass filter, which we're not going to be using, so we're going to ignore this one as well. Okay, acceleration data rate selection. Okay, so this is a register that we're going to be using to adjust the data rate. So let's go ahead and record this. And the address is 0x20. Again, because we're going to be writing to it, the topmost bits are going to be 0, so it's going to be fine. So this is the one that we're going to be using to transfer data across. So 0x20, let me just get that into decimal form. That should be 32. All right, and then we're going to figure out exactly what we want to set this to. Okay, so we know the data rate selection default value is 0. We can look at the table, what we want to set it to. So let's just say we want to set this to 100 Hertz as one of the options. So 0, 1, 1, 0 for this little set of data. So that's actually the top four most bits, as you can see right here. So AODR3 to AODR0 is the data rate selection. So that's 0, 1, 1, 0. Let's just go ahead and use a calculator and just punch that in. So 0, 1, 1, 0. Next one is the block data update. It's a continuous update array, so we're not going to change that. Let's see. This is the z-axis enable, so the default value is 1. So we want to actually enable all of these as well. So we want to actually set all these as 1 as well. So this means we're going to set this to 1, and this to 1, and this to 1. So that's going to be the bottommost 3 bits. All right, so it's 103 is what we should be setting it to. And that'll pretty much set the data rate to 100 samples per second, and it'll enable all of the axes for it to be read, to actually be reading data. Okay, let's look at the next one. Anti-alias filter, full scale selection. We're going to be using this one. SPI interface, we are going to use the 4-wire, and by default it's 0. This is going to be 0 as well. Okay, so the full scale selection, let's look at this. Okay, so we can do a few options. So we can make it so that it's plus minus 2 Gs are the maximum values that I can detect. Plus minus 4, plus minus 6, plus minus 8. We'll use plus minus 4 just for the sake of this demo. So plus minus 4, and let's see, locate that. So AFS 0, and everything else is 0, 0. So AFS 0, so AFS 0 is right here. So that's the lower 4th bit. So if I go ahead and erase this and set this to 1, and everything else I believe should be set to 0. Yeah, everything's going to be set to 0. So this is, in this case, we're going to set that to 8. So control register 2, which is 0x21. I believe this is 033. This should be 8. And let me just go ahead and double check if 0x21 is 33. So yeah, it is 33. Okay, so that's the next register we're going to be changing. Let's go ahead and go to the next one. Control register 3. Okay, these seem to be all for just the interrupt, so we're going to be ignoring this as well. Control register 4. This is also for the interrupt, so we're going to be ignoring that as well. Temperature sensor enable. Okay, here we go. There's a few things that we can adjust here. So we can actually change the resolution of the magnetometer. I think just for the sake of this demo, we're going to just be using the low resolution option. For magnetic data rate selection. Okay, so there's a table for it. Here's the table. Let's go ahead and set this to 50 Hertz, just for the sake of it. So that means this is going to be So we want to disable the temperature sensor. We want to have this in low resistance. This is 0, 0, 0. And then we want to set it to 50 Hertz. So the topmost bit right here is this 1, and this 0, and this is 0. Okay, so the other ones are latch interrupt requests. We're going to set these to 0 as well. So this is 0, 0, 0, 1, 0, 0, 0, 0. So that means 1, 2, 3, 4. That means right here this is a 1. So that means we're going to be writing that to 16. So this is going to be for control register 5. All right, the address is 0x24. I believe this is 37. Actually, it might be 36. Try 36. We'll go ahead and just double check that later. And we wanted this to be set to 16. Okay, so 0x24. That's 36. Okay, I'm right. And I'm just control register 5. Okay. Let's keep scrolling down again to find more other options that we can actually set to. So, okay, let's look at this one. Okay, for the full scale selection for the magnetometer. All right, so we want to adjust the the maximum values that it can pick up. So in this case, by default, it's 0, 1. So it's going to pick up plus minus 4 gauge at the maximum value. So I think we actually want to keep that way. Actually, that's not that bad. So I guess it'd be nice if we actually changed it just so we can actually just prove a point. So we're going to go ahead and write this we'll just go ahead and just rewrite this again to just plus minus 4 gauge just to prove a point that you can in fact adjust the full scale of the magnetometer. So I'm going to say control register 6 is going to be 0, 0, 1. 0, 0. So let me go ahead and just write that in binary form. So 0, 0, 1, 0, 0. So that's 32. Should be 32. And the address is 0x25, so there should be, I believe, 37. Okay, let's see if we need any of these. Okay, so there's this thing called sensor mode selection. So let me go double check that. Table 4091. By default, it is 1, 0. So that means by 1, 0, it means the magnetometer is in power down mode. So we don't want that. What we want instead is either continuous conversion mode or single conversion mode. So continuous conversion mode means it's actually going to be constantly reading in new data. Single conversion mode means it's going to read only once until you want to access and read it again. So we actually want to put it into continuous conversion mode because it's just a lot easier to read data out that way. So that pretty much means that, okay, so we want this to be default 0, so we don't actually want this on. Actually want it in normal mode, and then this is going to be set to 0 as well. We don't want it in low power mode, so let's see. By default it's 0, which means it's not in low power mode, so that's also 0. And then this means that we want to set to continuous conversion, so pretty much we're going to be writing this as just 0. So control register 7 is going to be set to 0. And the address is 0x26, which I believe is 38 in decimal format. So 0x26 in hexadecimal is 38 in decimal. Okay, good. Let's keep scrolling down and find more things about the status register for the accelerometer. We don't need this. This is for the interrupt. Okay, here we go. So the output data. So this is for the accelerometer data registers. Just to make it so it's a lot easier to type up, I'm just going to go ahead and just copy this. Just put it down here, and we can just change that. Okay, so this is also A. All of these are A for the accelerometer. For the x-axis acceleration data, you can see that it's 0x28 and 0x29 are the register addresses. Again, we're going to be doing the multiple read option, so we're actually going to be reading this and this consecutively. So we're going to go ahead and say it to find 0x28 and then add the topmost 2 bits to set to 1. That's E8. And if I convert this to decimal mode, that means it's 232. Right, so the next one is the y-axis acceleration data. So that's 2A. And 2B are the 2 register addresses. Again, we want to just read the first one and do the multiple byte read. So we're going to say 2A, and instead of top two most bits to 1, that's EA. And in decimal format, that should be 234. Okay, so the next one is for the z-axis. Ooh, that was a typo right there. Didn't catch that. This is actually for the z-axis. Okay, Okay, so the next one is 0 to C and 2D. All right, so we're going to go ahead and type in 2C, get the top two most bits to 1, so it's EC, and this should be 236 if I'm correct. Yep, okay. So that's the accelerometer stuff. Let's go ahead and check if you want to actually manipulate anything else from the other registers. So this is for the first in, first out data storage option. We're not going to be using that. We're not going to be using this either because it's for the first in, first out register. Int pretty much means for stuff for the interrupt, and as you can clearly see, this is all for the interrupts. So we're not going to be using this one either. Here's another one for the interrupt. We don't want to use this one either. Okay, interrupt threshold, we don't want to actually use the interrupt, so we don't need to bother with that. Duration value for the interrupt, we don't need that either. We don't need this one either because it's also for the interrupts. We don't need this one either because it's also for the interrupt. We don't need this one either because, again, it's for the interrupt. This is also for the interrupt. As you can also see, there's actually a typo here. So interrupt generator 2. So it says interrupt 1 threshold. It should be interrupt 2 threshold. So click configuration. We won't be using this. But the idea behind this is that you can also use the accelerometer to pick up taps. So if you actually tap on the accelerometer, like you can actually make it as like a button. So in one case, what you can do is actually do a single tap and a double tap. So that's what the click configuration does. It allows you to do that option, but we're not going to be using that option for this demonstration. You can use it if you want for your own project in particular, and you can just go ahead and just investigate this out. But for the case, again, we're not going to be discussing this too much in detail. Okay, so click SRC. We don't need this one either because it's for the tap generator, or the single tap, double tap option. This is for the threshold of the taps, time limit, time latency, and time window. These are all for the click options, the tap option. So we don't need these either. Active threshold. Yeah, we don't need this one either. Active duration. We don't need this one either. Okay, so we're actually at page 70 of 74. So we pretty much got through every single page here. Now just scrolling down, it's just package information of exactly the size and dimensions of the chip. So we're actually pretty much done here. So we're going to go ahead and just use this data and just go ahead and figure out exactly how our code should be written up accordingly.